Yeah, okay, cool. Okay, so what I want to showcase is I'm going to start with the bottom line being what is the end result, and then I'll go back in time and show how you can get to something that is this complete. So this is our master model that we use to design the 2019 intake for our robot backlash. I'll just pull up a photo so we can see an image of it. Oh, you're right. The photo will have the wrong intake.
I just show the intake.
Well, okay, fine. Yeah, we'll just show the final intake here. So this is the master model, and then here is the intake. If it flicks over. So this is the intake CAD for the 2019 intake. And this has way more detail than the master model, obviously, right? Like this has every little button head screw modeled in. It has belts, it has wheels, it has motors and motor controllers. But the key geometry of these polycarbonate side plates, the location of this roller, the location of these wheels for this claw, all of this was defined using a master model, which is, if you look at the feature tree on the left, it's basically a bunch of different boss extrudes, and they create a bunch of different solid bodies, one for each different part. So I'm going to show you how to get to something like this at the end. And so here's the real quick fly through, just to give you a sense of the order of operations here. So I'll get to the master sketch in a second. So I imported a sketch, which I'll show you how to do later. And we start by extruding some tubes. We extrude the polycarb side plate. We extrude this box tubing. We start throwing the top plate for the horizontal claw. We do a bunch of fillets. We do a bunch of mirrors. We make the other side. We start adding holes to mount the claw to the robot. We add this mount block. We do some more extrudes. Let's just keep going fast here. We have this plate that mounts it to the robot on the arm side. All this stuff coming down, mirror it across. Bunch of tapped holes, right? The major reason that I like to do master models, I'll explain in a second, but having all the holes defined here means that all your holes will always line up because they're all defined relative to each other. You don't have to manually go update them all. And so that is kind of how, skimming through the feature tree, I got to the end here. So we're going to come back to this at the end of the talk, but first I wanted to just kind of showcase really simply what are the core principles we're talking about. So I'm going to make a new part. I use a lot of keybinds that I can talk about at the end, but we're going to go pretty fast here. So we're going to make a relatively simple part to start, then we're going to make a gearbox, and then we're going to do the fun stuff of making it into a master model. So super simple part. Let's just make a block. I want a block, so I'm going to do a center rectangle in the middle. We can dimension all these things. We can extrude it about the midplane. We can save the part to not the folder full of the robot. Let's go into here. Let's call this block 4. Okay. So here's the first extrude. That's pretty simple. I think if you've done SolidWorks before, you're pretty confident with making a single body. The real trick now is about to happen when we try to do the second body. So let's make a piece of, let's say, box tubing that this block slides inside of. So I'll sketch on the front plane, which is in the middle of my part because I did a mid-plane extrude. Sketch on the front plane, and what we can do is I can click on this surface. I'll do offset entities of like maybe 10 thou or something, and then off of that we'll offset entities 1/8 of an inch. So now we have a box tube that's just a little bit bigger than our original thing, and see, we're defining our geometry of the second part based off of the first part. So now here comes the real trick. When we hit extrude, we are gonna again just do a mid-plane extrude, make it kind of long. Oh, I clicked bad there. Okay, so here's the thing where people, by default, this checkbox, merge result, is checked. And if you keep that checked, when I hit enter, these become one body. Did it work? Oh, they're not touching. So it, oh, okay, yeah, you're right. Because I built in an air gap. Okay, fine. Pivot. Here we go. Let's do it even more simply. We don't even need to make a sliding block.
Make like a cylinder on top.
Yeah, let's just make a cylinder on top. Okay. Sketch on the top plane, draw a circle, dimension that, 1 inch, extrude it up 1 inch. Okay, these are touching. If I just hit the check mark, these are going to merge. There's not going to be a bodies folder over here. These are one body. A good way to check if they're a body is if you're able to do a fillet between the two, then it's going to be a single body. Okay, because it's able to cross that boundary. If we want to have two bodies, back when I'm making this feature and I'm in the final steps of doing the extrusion, if I uncheck this merge result button and then hit the checkbox, now we have two different bodies. The solid bodies folder appeared in the top left. I can select the two different bodies. You can also hide and show bodies independently of each other. So you can like go to the bodies folder, you can right click, you can hide it, you can look at the underside of this part, you can right click, you can show. You can also do hide and shows. I like to do them with the tab button, I think is a default keybind. So if I mouse over this block and my mouse is over it and I hit tab on my keyboard, it gets hidden. Shift tab will make it reappear where my mouse was. This is important when you start getting a bunch of things all really nested inside of each other and you have to hide all the crap out of the way so you can see the thing you're working on. So that's why I demonstrated that. Okay, so we have our two bodies. Now what we want to do is export them into individual parts so that we can actually make a part drawing for them to send to our machinist team, and the machinist team can then make the parts. So how are we going to export this single part file into multiple part files? There's a couple different ways of doing it. So I'm going to show the easiest method first, and then I'll work my way up to the slightly more intensive but more robust method at the end. So the easiest method is you just come into the solid bodies folder, you right click on a solid body, and you click insert into new part. And what that'll do is bring up a little insert into new part button, feature tree. It's saying I will transfer this solid body. I need a file name, so I'll click on the browse button. I'll navigate to the folder I want to save it into. I'll call this, lower block or something. Hit save, hit the check mark. And now it's created a new file name called lower block. And the only feature in this file is this external reference pointing back to my original multi-body part. Let's go and do the same thing for the second part, and then we can put them together in an assembly. So I'll use Control-Tab to cycle my way back to the multi-body part. I'll click on the second multi-body, insert into new part, save it into the same folder. I'll call this upper cylinder, check mark. Now we have our two different parts, lower block and upper cylinder. I can click, File, Make Assembly from Part. If I click the checkbox here, it'll insert the part into my assembly that I want. Go back to Assembly, Insert Components, choose the upper cylinder. Now here's what's interesting. If I drop this anywhere, it'll just drop in. This is classic inserting components, doing mates and assemblies that all of you are probably familiar with. If I just drop this anywhere, it's not going to have any mates. It's going to be free floating. I can constrain it with mates. One of the other great things about the master model, the multi-body model, is that all of your parts are being extruded and defined relative to an origin. So I don't actually have to go in and mate this thing. Another way is if I don't want it to move and I want it to stay fixed, I can click Insert Components, find my upper cylinder. If I also click the check mark, it will locate this cylinder relative to its origin being the origin of the multi-body part that we started with at the beginning. So this is really handy because it means that you can build your assemblies super fast without having to go and do all the assembly and mating. The downside is that when you do this, this thing is fixed, so it's not able to, like, if it was like an arm or something, you wanted to show it rotating, it's not going to be able to rotate. But I think this is really handy for, like, if you have a gearbox, you don't really need to see the gears in the gearbox spinning. You can model it all as a single big multi-body part, export it all, and just check mark, check mark, check mark, and they all just get fixed in place, all perfectly aligned how you intended it in the master model. So this showcased what I would call the first and simplest method of doing multiple bodies and then saving each individual body as a part and then reassembling them yourself. I'm now going to pivot and show another slightly more advanced way to do this. But I want to, actually I should have saved that. Anyway, does anyone have any questions on that? Yeah, I'm happy to stop. Yeah, go ahead.
Why would you save files and then reassemble it as the original model?
Yeah, so the reason is if I want to get the thing machined, I want to send a two-dimensional part drawing to my machine team. So if you have done drawings before, I'll just make a really quick one here. You want the drawing to be of just your singular part. You don't want to send the entire multi-body part for them to try to machine. It's much harder to digest. So that's the main reason why I want to at least break it up from multiple bodies into individual parts. The other reason is if you want the thing to move. So if I go back to the multi-body, these things are literally extrudes. There's no way that I could ever move them. So if you're doing something like an arm that you want to see the different scoring angles of, or you're doing a pneumatic cylinder that pushes a linkage to deploy a thing, or like an intake that folds down over the bumper or something, there you want to design it in one of the states, extrude it all, then turn it into an assembly and move it through its range of motion and make sure that there's no collisions or see the gravity effects on it, whatever you want to do. So those are the two reasons. Does that answer your question? Okay. Does anyone have any other questions so far? I'm going really fast here, but I want to leave time for the cool stuff at the end. Okay. So that was step one, was multiple bodies, not merging entities, and then exploding them and reassembling them. There's another way to do this that's similar to what I just showed, but it makes it a little bit faster. So if you feel like you've done your master model and you're all done, you've really reached the end, and you want to just very quickly do all that, creating files, generating individual file names, and reassembling them, you can use a feature where if I right-click on this folder and I click Save Bodies, it will do that Save Bodies on all of the bodies in that folder. So now you can see we have a row per body. I can click the save mark and it's going to start saving them. It doesn't know what to name them. It's naming them what the features are. Boss Extrude 1, Boss Extrude 2. I can come and double click in here and I can name this, lower block 2, because I'm just trying to avoid duplicate file names, and come up here, call this upper cylinder 2. So now it's basically taking that thing we just did and doing all of them at once in a really quick button. Create assembly, we can come in here and call this, block assembly 2, and then we hit the check mark. And now it's going to create each of the parts. Here's the upper cylinder. We'll rebuild this. Okay, so a lot just happened there. Let's see what it did. My original master body part, block 4, now has a feature at the end of it called Save Bodies. If I edit that feature, you'll see it's just the options we just selected there. Okay. If I click the check mark, it's going to rerun all those commands. Okay, what else did it do? It created an assembly with lower block 2, upper cylinder 2 fixed in place, just like how they were in the master model. But now they're individual parts. I can open each one. I can make a drawing from it. I can move them around if I undo the fixed and, dimension them and stuff. Like here, we can show that real fast. So let's say I want to have this, you know, this is a pivot point of a big arm. It's going to sweep 45 degrees. I can, you know, come in here, dimension, make a slot or something. I don't know, just kind of going fast. Make it a 6-inch long arm. We'll make this and that have the same radius by making those circles cordial. We'll extrude this. We'll extrude it up. We won't merge result. Or no, let's merge result. So here's a good lesson. So when I click merge result, you'll see this extra tab appears at the bottom, feature scope. And right now it's on auto selecting the bodies. If I uncheck that auto select, I'll get a little window where I can choose what bodies this feature's scope is. Scope meaning what this thing can affect. If I only select this body, it will, okay, well this isn't a great example because it's not going to impact that anyway. Let me just do another good example here. Okay. If I want to cut, a classic example of this whole feature scope thing I'm starting to talk about here is if you want to do cut extrudes or holes, and you want the holes only going through some of the bodies but not all the others. You don't want to cut extrude through your entire assembly. You just want to cut extrude through one of the bodies in that assembly. So here's what we'll do. We'll say that this upper crank is attached to this lower block with a counterboard socket head cap screw above that is tapped into the lower block. So we're going to need 2 hole wizard features. Let's do them. So I want a hole wizard feature, hole wizard up here. We're going to choose a counterboard for a socket head cap screw. Make sure you change that from binding head or whatever the heck that is. Sure, no, 1/4 inch bolt, close fit, condition through all. We'll turn off the countersink. And then here's the important part, feature scope. It's going to go through all, but I only want it to go through all through the crank body, not through the lower block. So I'm going to undo auto select and select the body that I want it to have feature scope on. Then we can go to positions, click on this face, drop in our hole. And now it looks in this preview like it's going to go all the way through that block. But because of the feature scope, when I hit the check mark, it's not actually going to cut that at all. It's only going to do the counter bore and the upper hole. If I hide this lower block, you see it went all the way through. But if we hide this, you can see it didn't touch the block at all. So now let's say we want to do the tapped hole. This is where the good, the good parts of master modeling come in. If we do hole wizard, tapped hole, 1/4-20 through all, positions, click on, maybe this face, go normal to, select the same spot. In this case, they both happen to be on the origin, but you could imagine that if they weren't on the origin, I could select all the circles of where all the other holes were, and they'd all go to where those holes are. Again, making sure all of your holes line up, which is a great feature. Hit the check mark. Oh, no, sorry. We have to go back to type, feature scope, select this body, check mark. And now we have the tapped hole going just through this and not through that. Counterbore, tapped hole. Cool. All right. It's pretty funky. Like, you can come in here, you can sketch in some weird, extruded cut that looks like it's going to destroy both things, but then I feature scope and only select one of them, and the other one remains unharmed. I don't know. It's like it becomes a ghost or something. It's kind of cool to think about. Okay, so now that we have these extra features in here, I just wanted to showcase basically this. So if we save this, we go to our assembly, we rebuild it. This is not good. This thing. Oh, it's because the feature's earlier. Haha! Okay. Here, let me go back. I figured out what I did wrong. So, see how there's this save bodies feature? It happened first, then I added the link arm and all these feature holes. if I move this to the end, what it'll do is do this step last, meaning it'll have all these extra changes in there. So if I go back to my assembly now, we should rebuild, and we'll see that our body updated. So now we have the counterboard hole and the tapped hole below. So as to the point of, maybe you want the thing movable, you can right-click on this feature, float it. Now it's totally unconstrained, and we can go in here and do the necessary mates, maybe concentric mate between the actual holes. So we'll do a concentric mate here to there. Check mark that. So now we can actually move the thing around. It's not completely fixed. So this is, useful, like I was talking about, for visualizing your range of motion of an assembly. Okay, so that was kind of technique number 2, using the save bodies feature to kind of export everything all at once. Does anybody have any questions or comments or concerns on that? You guys give me a nod of the head if you're starting to see the usefulness of this multi-body stuff, especially when it comes to those like tapped holes. Like that's a pain in the butt to like recreate hole patterns on a bunch of different parts. Okay, cool. Let's now go to the layout sketch design, and that really, I think, is where the real power comes in.
There's one more.
There was one more? What was there? What am I missing?
Bodies.
Oh,
if you want to go over that.
We'll do that when we do the layout sketch.
Okay,
we'll do both, because I kind of need a layout sketch for that. Anyway. Okay, I'm going to close a bunch of this stuff. Yeah, we'll do the pros cons at the end.
Alright, sure.
Okay, so far we've shown how to save an individual body as a part. We've showed how to save the entire set of bodies as individual parts and automatically create an assembly for you. Now what I want to do is show you this master, what I'm calling layout sketches. Holy shit. Let me do this. So what is a layout sketch? A layout sketch, or a master sketch, is where you have a bunch of sketches, a bunch of complicated sketches that all are doing a lot of the key geometry definitions, instead of you defining each part with its own dimensioning, going to the assembly, checking if it works, adjusting things on the fly. You kind of define it all right the first time. So here is the master sketch for the top level assembly of our entire robot. If you guys have seen the 2019 robot, it basically is a drive base with an elevator here that's mounted onto a little turret. And then on that elevator, there's a double jointed arm, which has a shoulder. Uh-oh, not good. Error message. There's a shoulder and a wrist. So this giant sketch is basically trying to show, what does the intake look like when it's intaking a ball? What does it look like when it's intaking a disc or scoring a disc on the cargo ship? What does it look like when it's scoring a ball on the angled ramp of the cargo ship? What does it look like when it's way up here scoring a ball and a disc on the high level of the rocket? So we're kind of, in one sketch, I'm drawing all the different scoring states, and then I'm using the scoring states to define how long the length of the arm is, how big the rollers are, what it looks like at the ground, what it looks like up high. So it's kind of using the end goal to define how the thing should be designed, rather than the way most people do it, which is you just guess something that you think will be pretty good, or you have a prototype that tells you it's somewhat good, and then you kind of check it all and go into the assembly, go back. So it reduces iterations. So the point is this big layout sketch is what is driving our intake geometry. So if I go back to our 2019 intake here, you can see that the first feature we did was we insert part on that sketch. And this looks like super crazy because there's a bunch of different sketches going on. But if I would just roll back to the top here, if I edit this feature, actually, let me just do it from the beginning. Let me do it from the beginning. We inserted the body, then we, this is just convert entities, or I'm not sure.
No, it's just defined off one of the sketches.
Okay. It's been like a couple months
sketch.
since I've looked at this. Anyway, I'm gonna get back to this. Let's just start from the beginning on a layout sketch that drives a master model that drives a bunch of different parts. So let's just do a really simple gearbox. Custom gearboxes are something we do a lot on 254. Maybe you aren't doing a fully custom gearbox. Maybe you're having a motor drive a versaplanetary that drives, the sprocket and chain for the final output. I think most people could use this type of skill set. So if we make a new part, and let's just do a simple sim motor driving some gears. And in this presentation, we're also going to go through some good modeling practices. I'm going to sit down because I'm getting tired. Okay, can everyone still hear me even though I'm behind this thing? Oh, there it's a little better. Oh, okay, here we go. So let's start sketching on the front plane. Let's design our gearbox. Let's make it so the output is a sprocket. So we're going to draw in a circle, dimension it. What do we dimension it to? Let's choose the pitch diameter of a number 25 chain sprocket. So I don't know what that number is. I'm going to go to Google. I'm going to look up VexPro sprockets. On Google, we find the VexPro sprockets page, number 25 sprockets. We scroll down, we go to the drawing section. Here's number 25 sprockets with hubs, and it has this little table. It tells me for a given tooth, what is the pitch diameter, the outer diameter, the diameter of the chain, the bore of the thing. So maybe I want my output to be a 16-tooth, half-inch hex, number 25 sprocket. So my pitch diameter, it tells me, is 1.273 inches. So we go back to CAD, I type in maybe 1.273. And then here's the key part that I like to do when I'm doing gearboxes especially, is I convey design intent by labeling my dimensions. There's two ways to do that. Here, I'll show you my favorite way, is you just leave the dimension as it is, but over on the left side is the dimension text box. You click in there. I like to click enter so it goes on the next line. And then in here I can type in something like number 25. I use all caps because that's the American standard for it. Number 25 sprocket, 16 tooth, PD, standing for pitch diameter. So I'm adding this little note on the dimension text. And now it adds that little dimension label here in my sketch. So later on, I'll remember what that circle is. Does anyone have any questions on that? Because that, I think, is a really useful feature you can use even in any type of modeling SolidWorks practice. Okay, cool. This 16-tooth sprocket, let's say it's driven by a maybe like a 50-tooth gear. So I might come in here and say this equals 50 teeth divided by 20 because I want a 20 diametral pitch gear. Here I'm assuming you kind of know how gear pitch diameters work. I'm going to draw in all the pitch diameters of all my gears, and then if I make all the pitch diameters tangent, then all the gears will have the right center distance. The way that you define the pitch diameter, the size of the circle that the teeth mesh on, is you take the number of teeth and you divide by the diametral pitch. The diametral pitch is a constant that is literally relating the circumference of the gear to the number of teeth. And in this case, the diametral pitch of these VexPro gears is 20. They also sell 32 DP gears, but those are better for like little small gearboxes and not for something that I'm driving like a big robot arm off of. Yes?
Do you know how, like, what's the specific thinking or process to know if a gear matches with another gear?
So it's basically only two factors that you need to concern yourself with. It's the diametral pitch and also the pressure angle, which if we go into their 20 DP half-inch hex bore gears page, we see it says that they are 20 dp with 14.5 degree pressure angle. Almost always, the pressure angle number will either be 14.5 or 20 degrees, and that's basically kind of a constant throughout the industry. The difference in the pressure angle affects the strength of the gear tooth, with 14.5 being, I think, stronger, like a little chunkier teeth. 20 angle being a little bit of a finer rolling motion, a little quieter, a little less backlash, but not as strong teeth. So the 20 dp, this really is a reflection of how fine the teeth are. So if I just go back, or here, we'll do this. Duplicate this tab. Go back to gears. If we go into their 32 dp gears, oh, here we go. So you can see the 32 dp gears have a lot of little fine teeth. The 20 dp gears have wider, chunkier teeth. That doesn't really show that well in this image because that's a 60 tooth gear. There's a bunch of tiny fine teeth, larger, chunkier teeth. Anyway, I don't want this whole talk to be on just gear design, but since we are making a gearbox, it was a little important to make sure that we cover that. We're going to use 20 dp gears everywhere. 20 dp, I want a 50 tooth gear. I'll make an equation equals 50 divided by 20. Hit the check mark. We can come over here and we can label this 50 tooth 20 dp PD. So this is a 50 tooth gear with 20 diametral pitch, and this is its pitch diameter. Hit the check mark. Now we have our second gear. Now let's go and draw in the next gear in the gearbox. Maybe this is a 14 tooth equals 14 over 20. Hit the check mark. We'll label this 14 tooth 20 dp PD. And now if I make this circle and this circle tangent with each other, this will make sure that the center distance between those two gears is correct. The gears will properly mesh. They won't bind, they won't skip. Lastly, this is still blue and undefined because I haven't located it with respect to the origin. It's just able to move around the circle. Maybe I'll come in here, select both of these, and make them horizontal with each other. Cool, that was our second gear. Now I'm going to keep working my way back to the motor. Maybe I need another big gear that drives this small gear. We'll dimension this one to be maybe like 44 over 20 equals 44. So the reason I'm using, let me explain one thing here. The reason that I'm using an equation here with the equal sign instead of just, straight up typing 44 over 20 and doing the math is because, again, this conveys the design intent better. If I double click on this dimension, it says 50 over 20, where it's, rather than it just saying 2.5. Like, where did that 2.5 come from? I use the equation to convey I'm intending this to be the number of teeth divided by the diametral pitch. That's my pitch diameter. Okay? So here I'll do that again. Over here, 2.2 equals 40. Let's go smaller. 40 over 20. Oh, it didn't make an equation because I wasn't in the full equation editor. You have to be in this pop-up box. Equals 40 over 20. Now it's an equation. We can come over here and label this 42 20 dp PD. Okay, so we're slowly building out our gearbox here. Let's do the drive pinion and call it a day. So what type of sim pinions can we get? Maybe we go back to Vex Pro. We go into here, 20 dp motor pinions. We see for a sim motor, we can put let's do a 12 tooth aluminum spur gear. Cool. So we'll come in here, define this. Equals 12 over 20, 12 tooth 20 dp PD. I also like to just say it's a sim pinion to make sure I know exactly what that gear is. Make these two tangent, make this horizontal relative to the origin. Okay, cool. Now my main layout sketch is done. Maybe it's helpful for me to draw in some other things. But this is really the key of the gears. So let me save this. Let's call this gearbox layout sketch. If you want to add more detail, you can. I recommend trying to, if you can, stack your sketches on top of each other in cases where it makes sense. So in this case, I want to sketch in, let's say, the diameter of the body of the sim motor to make sure that the motor won't collide with anything. So if I could either do that in this sketch by drawing a circle in line with the sim pinion and making it be 2.5 inches or something, the diameter of the sim. But now this sketch is getting kind of complicated. I've got both gears and motors going on in this sketch. Another way to do this is to just make another sketch that's on the same plane. And on this sketch, I diameter and drop in the 2.5 inch. And this is the sim body outer diameter, OD. So now we have a sketch with the sim modeled in there. And maybe the sim has a mounting bore. I think that is like 0.755 or something. I don't know. You have to kind of measure the sim to get all these numbers. So this is sim boss bore OD. So now I've dimensioned the things that my sim motor cares about. And now I'm getting all these different sketches over here. So I again want to convey design intent. You can rename sketches, features, put things in folders. How do you do that? You click on the sketch, click it again, and it will bring up the little rename option. In here I can type in, this is, gears layout. And then in this one, I can name this motor mounting or something. And you can keep adding features. I want to do, let's do this next. Let's say now we want to make our gearbox plate. Oh, let me do one more thing. I'm going to sketch on the front plane. I'm going to do all the bearing bores. So that I want ball bearings, Vex Pro ball bearings, holding all of the shafts in my gearbox. Maybe I'll come in here and I'll dimension in a 1/2 inch bearing here, which has a 1.125 bearing bore. So this is a half inch bearing bore. Then this shaft is gonna maybe want a 3/8 inch gear, 3/8 inch shaft. So I'll be like, I think that bearing bore is 875. Obviously, if you don't have all these numbers memorized, you have to go look them up every time you want to do this. It slows you down a lot. So I've been doing this a lot. I have these numbers memorized, but I'm not expecting everybody to have it memorized. But you got to start somewhere, right? So this is a 3/8 inch bearing bore. 3/8 inch meaning the diameter of the shaft that goes into this bearing. And then over here we had the motor mounting, which we'll just leave that how it was. So now we have our bearings. Come in here, we'll call this bearing bores. Okay, cool. So this was our layout sketch. Now, there's a couple different ways that we can turn this layout sketch into our actual gearbox. And I'm going to try to, in the next 45 minutes, showcase as many different ways as possible and talk about the pros and cons. So to do this, I'm going to basically make a bunch of different copies. We're going to have number 2. And let's do number 3. Okay, that's enough for now. Okay. Before I go any further, does anyone have any questions on just this concept of doing a sketch, using equations to convey design intent, labeling dimensions to convey design intent, if it makes sense, stacking dimensions driven off of earlier dimensions? Everyone seems to got that. Okay, so let's turn this into a gearbox. How are we going to do that? I will do the first method, which is I'm going to import the layout sketch into any part that needs it. So in this case, let's do the plate, the gearbox plate that holds the motor and a bunch of the bearings. So what I'll do is I will make a new part, Control New, 254 part template. I will save this part as motor plate. I'll label it 1 so it matches with the other one. And now here's what we got to do. We got to come up here to the pop out. We go to insert, come down the part, insert part, and then we navigate to the folder, find the necessary part. In this case, it's this gearbox layout sketch here. Click open, and now it's trying to insert it. What I want to do is select all the right checkboxes on the left-hand side. Here's what I personally almost always choose. I import solid bodies. I import no cosmetic threads. I don't import any of this stuff. I import unabsorbed sketches, and then whole wizard data. So what is the only one that might be confusing here is unabsorbed versus absorbed sketches. Basically, if your sketch gets turned into a boss extrude or a revolve or a cut extrude, that sketch is now absorbed into that 3D feature. If you don't do that, like we did with our sketch here, where we just have sketches as their own, not turned into extrudes, then these are now considered unabsorbed sketches. And when we insert them with this insert part feature and click the checkbox, we get a feature in our new part that is our layout sketches. Under it, you see we have a folder for all of the sketches that we imported. We still have all the labels on all of the sketches, so we're keeping all that work that we've done with us. And now we're in a separate part, so we can do the gearbox plate design and not mess up our layout sketch and clutter up that master model. So gearbox plate, maybe this is really simple. We'll just come front plate. We'll just do a little plate like this. So I'm just grabbing the kind of the outer diameters. In this case, that was a pitch diameter, so we'll grab the outside of it with the outer diameter offset. I'm not going too much into detail on these gearbox things. Make all these lines tangent, so it's like, it looks nice and swoopy. Okay, and then we want to grab the bearing bores. Oh, which one's which? Good thing we labeled our dimensions. I can go into here and scroll through, and I can hide this thing on the gears, hide this thing on the motor mounting, and I just want to deal with the bearing bores. So now I can make sure I grab the bearing bore. Yeah. Sure, we can do pocketing at the end. We extrude this gearbox plate. Maybe we do a mid-plane extrude because we like to keep our planes in the middle of our parts. We choose a 1/4-inch gearbox plate. Now we have our gearbox plate. Diego asked about pocketing. If you have a heavy part, if you have a heavy plate, you want to reduce some weight, maybe you come in and pocket things. I'm going to do the really fast pocketing demo. We use offset entities to define web thicknesses. In recent years, we've been using, for a 1/4-inch plate, we've been doing 0.14 is what we found feels about right in terms of the size of the webs. So I do an offset 0.14 on the contour. I do it on each of the bearing bores that are going through my hole. I do it on, and then I draw in some maybe construction geometry. Maybe we do it like this. We draw in all these construction lines. This is just how we do it on our team. There's a bunch of different ways. Maybe this guy also goes up here. In general, when you're pocketing, I like to have things constrained by at least 3 ribs, so that it's kind of 3 that are kind of at least in like a triangle. If not, 4 ribs is better. Here we have 4 ribs on everything. Offset entities, bidirectional, divide that number by 2, so we get a bidirectional offset on each of these ribs. Select all these construction lines. Boom, 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 boom. check mark it, extruded cut, select all the pockets, cut through all, check mark, pocketing, come in with the fillet feature, grab a vertical edge, select all the edges, make it 0.13 or something so a 1/4 inch end mill can get in there. Now we have a pocketed gearbox plate. This wasn't a demo on pocketing, so I don't want to go too far in detail, but does anyone have any questions on that? Because I did show a lot of cool features there. Offset entities, the fillet feature to select a whole bunch of stuff at once. Does anyone not follow that? Yeah. Do the fillet again.
Just example of what all the other three buttons there did.
Yeah, okay. So I'll delete the fillet feature. Diego, you were asking about the fillet feature. Okay. I'm going to redo the filleting. The reason we do the filleting is because you have a little circular end mill. It's not going to be able to cut these sharp corners. And also these sharp corners are stress risers. It's a concentration of all the stresses into this little point. If you have fillets there, it allows the stress and the strain to distribute around the fillet. It makes your part stronger. So I'll click the fillet button. I'll type in my number, 0.13. I'll select one of these little vertical lines, and then this pop-up appears next to my mouse. If I go through each of these, it says connected to the start loop. So it's going to do everything inside of that first pocket. That's sometimes useful. The second one is connected to start internal loops. So it'll grab all the vertical edges on all the loops. Then there's even more options. This one grabs basically all the edges. This one grabs all the edges that are connected to this edge. I don't know. You basically mouse over and see which one is right. You don't have to memorize the names. In this case, I wanted to grab all the pockets of all the spots. Click them all. It shows the big preview. Click the check mark. We're good to go. That's a new feature as of SolidWorks 2016. So if you're on super old SolidWorks, you won't have that. Anybody else have any questions on this gearbox? Okay, cool. So we have our motor plate. This is awesome. Now, if we wanted to actually turn this into an assembly, we could, but what I'd like to do actually is showcase why we even did this as a master sketch, inserting it around. What are we even gaining from this? The gain comes when you start to have multiple parts and you want them all to be related to each other. So in this case, my gearbox is going to consist of a mount plate that I'm calling the mount plate, the plate that mounts the gearbox to a piece of box tubing or something. And then the motor plate is the thing that holds the motor. So in this case, we did the motor plate. Maybe we still need to go and do the mount plate. So if we go back to our layout sketch, maybe we need to sketch in here a couple things. Oh, I missed some stuff actually. I missed doing, this is the sim mount holes, CC. So that's for the 1032 holes that mount the sim motor. And I also missed, well, that's for the sim. Okay, now let's do the mounting to the tube. So maybe we're going to have a box tube that's 2 inches tall. We can just make this kind of long. And this, let's just position this midpoint there, make that line horizontal, locks this in. We'll just dimension this. These are all kind of random because, again, you kind of have to know about the greater assembly you're dimensioning things into. So this is my box tube. Okay, now let's just mount to the box tube. So we're going to have maybe a bunch of bolts, like 1, 2, 3, 4. Grab those horizontal, horizontal, vertical, vertical. I have a keybind for horizontal and vertical. Oh, that didn't work. Wait. Oh, I don't. Yeah, there we go. Okay. Cool, 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 cool. Okay, dimension center. Center's here, maybe 3 inches. Yeah.
Are you more
run into the issue that it's gonna be exactly where the pocketing is?
Yeah, we'll have to update the pocketing. But this is for the mount plate, which is not the plate we just designed. Let's make this a little bigger. I don't know. Something like this. Whatever. It doesn't really matter. This is mount hole locations. Save this. If I go back to my motor plate, you'll see that it updated. It kept pulling in even the new sketches. I can hide them because I don't really care about them. But I guess I did care about, actually, sorry, I did care about this motor mounting holes. We have to go back to this. Let's roll back. Let's hole wizard some screw clearance. This is something a lot of people mess up on, actually, so I want to take a second here to make sure everyone catches this. When you're using hole wizard to make a through hole, a clearance hole for a bolt, a lot of people click on the hole button and then they leave it on drill sizes and then they scroll down until they find like a 1/4 inch, or they go and they find number 10 thinking it's the drill for a number 10 screw. American system is stupid because they have both numbered drills and numbered screws. And really what you want is the clearance drill that drills a hole a little bit bigger than the exact screw diameter you're about to try to fit in there. So in this case, you need to change this type drop down from all drill sizes. You change it down here to screw clearances. Then you choose size. Up here is number 10. So it's going to be a clearance, a drill to drill a clearance hole for a number 10 screw. Maybe we want close fit, condition through all, choose positions, front plane or whatever. Click these two points, check mark. Okay, now if I roll this forward, our convert entities didn't really realize that we added these extra holes. So maybe we want to come in here and offset. Oh, that's not good. Can we do this? Huh. Well, that's weird. SolidWorks is not feeling happy today. Okay, let's just draw in our own circle. .375 maybe. Make those equal. Checkbox. Now our fillet feature is going to be broken because it is missing edges. Come back in here, select a vertical edge, select all the ones we were missing, hit the checkbox, get through the error message. Okay, now we have the ability to mount the sim motor. Awesome. What do we want to do now? Now what we want to do is we have this box tubing and these holes for the mount plate. So now we can design the mount plate to also reference this same sketch. And then at the end, we'll do the real wow factor, okay? So we have our gearbox layout sketch. Let's do this. Let's come to motor plate 1, save as, let's make this a little bit better. We'll call this, yeah, okay, motor plate 1, and then save as, copy and open. We'll rename this mount plate 1. And you'll see that we still have our inserted layout sketch, but all this other stuff is kind of useless. So I'm just going to delete it all. And we can start from here again. I'll show all these sketches. We'll sketch on the front plane. Let's make a mount plate. Mount plate. We're going to want it basically... Actually, let me go back. Starting from here. So the difference between the motor plate and the mount plate is that the mount plate mounts to the tube and doesn't hold the motor. So I actually don't need this part that goes around the motor. Instead, I just need a little bit of material to hold the gearbox screws over here. So maybe we just come across, down, and back. Make these horizontal, make this vertical, choose an offset number there of like maybe ½ an inch or something. And then maybe make these lines tangent, and we're fully defined. Extrude this, midplane, ½ inch. So now we have our mount plate. Let's put in the holes. So maybe they're tapped holes for number 1032. Drop them in. See, I'm using the holes that we defined in the master sketch to define where they are in my new plate. Maybe we come in here, we round these corners because they look stupid. Okay, cool. And now, I'm not going to redo the pocketing again because I don't think it really matters. But now we have our motor plate and we have our mount plate, and both of them are defined back at the layout sketch. So now let's really quickly just make an assembly. I like to grab the mount plate as the first one that will be fixed. So File, Make Assembly from Part, choose our template, choose the mount plate, hit the check mark, insert components, motor plate, bring it in. Oh, I didn't design in any standoffs because I'm bad, but here we go. Make these bearing holes, let's say, concentric with each other. And let's hide sketches because this is crazy. Okay. Make this bearing hole concentric with that bearing hole. So now all of our bearing holes line up. And then because I don't yet have a standoff in here, I'm just going to do a distance mate. Don't sue me. Here we go. A 1-inch distance mate. Okay. We'll save this as gearbox 1. Okay. So now we have everything fully defined. We're super chillin'. But your prototyping team comes back and says, yo, your gearbox that was supposed to go super slow is currently way too fast. You need to go even slower. And you're like, oh shoot, good thing I have this awesome master model. So you just come in here and you can edit one of these gears. So in this case, we say, oh, okay, I want that to now be a 64-tooth gear to get even slower gearbox, more torque. Hit enter. Equation automatically updates. The only thing that doesn't update is our label, because I don't know how to do that. So we have to come in here and manually update that. So that kind of sucks. But everything updated, everything moved around. Exit sketch. None of this stuff broke. Okay, we still have the sim. We still have all these other things. We go to our gearbox assembly, hit rebuild. Okay, probably the pocketing broke, but it looks, for the most part, the holes are still lined up. The diameter increased to match the bigger thing. What broke? Probably this pocketing over here, because of pocketing is always kind of finicky. Let's see, am I right? Is it the pocketing? Oh, it's the fillets. Okay, fine. We'll fix the fillets. Okay, whatever. It's all good. Let's get out of here. Save it all. Okay. Okay. So is that cool? Like, you can update a gear. Both the gearboxes will update. Nothing, well, mostly nothing breaks. And then you have no chance of, like, mismatched alignments and stuff. So that is my preferred way to doing gearbox design. You don't have to do the, like, stacking the sketches on top of each other. You could, if you wanted to, sketch everything all in one sketch. But I do think that doing the layout sketches only, then inserting those sketches into the parts and designing the parts individually is the best way to do gearboxes. But I am going to showcase a couple other ways of doing the thing that we just did, okay? So let me close these other layout sketches that are older now. This was our best layout sketch, right? File, save as, let's make a copy. Let's label this one number 2. We can overwrite that old thing. Okay, what are some other ways of doing this besides inserting the layout sketch? Instead of doing the layout sketch technique, we can do the multi-body technique. So for the multi-body technique, you're basically going to stay in the layout sketch, and you're going, to do all of these things that we had done before. So I'm gonna just do them really fast here. Or maybe, yeah, go ahead.
Are you going to do standlines this time or standoffs?
Do I want to do standoffs? Yeah, okay, we can do standoffs. Yeah, so let's do this. We have our gearbox plate again. Convert, extrude, midplane, 1/4 inch. Okay, you wanted to do the standoffs? Let me just roll back and do the standoffs really fast. So maybe for the standoffs, we care about... Oh, let's just do them in the same spots that these are in. That'll probably work. I don't know. So, oh, they won't really fit. A standoff is like 3/8 of an inch into outer diameter. So that's going to hit that gear there, you see? And this one over here is having to go through that other gear. So that's not going to work. Maybe we can fit a standoff like up here. And then we'll do one here on the sim. These will be our 4. Or let's do them over here. Okay. Split midpoint. Horizontal. Define a center distance here. 2.375. Oh wait, that's not the outer diameter. 2.5. And then maybe a center to over here. 4.75. Okay, cool. Exit sketch. These are the standoffs. Roll forward. Edit this sketch. We need material where our standoffs are going to go. So what we'll do is just draw some arcs that follow the standoffs. This is annoying. There we go. Come on. Yeah, this is getting a little bit more detail than I was hoping for this workshop, but we're going fast, so I'm going to connect all these things up. Using the tangent keybind here. Okay. Okay, cool. Now we can do our screw clearances, number 10. So, yeah.
Probably want to do the standoffs and then screw clearance all the way through body, through all the bodies.
Oh yeah, that's a good idea, Noosh. Okay, so we have our sketch. Let's now do the standoffs. So the standoffs are going to come off of this plate, and they're going to be this diameter. We'll convert entities, and we'll extrude, and we'll make them 1 inch long, and we'll uncheck merge result. Let me actually, I'm gonna go even a little bit more advanced here to really show you the way that I would really do this. I would not just arbitrarily pick this blind standoff length. I'm going to do another layout sketch that gets us the ability to see from a top-down view what this gearbox is going to look like. So this is kind of doing layout sketches in one view and then looking at it from the other sides so that you can see, you know, the height and the depth and the width and everything. So we've done one from the front view. If we do another layout sketch from the top view, it's a little tricky. If I spin myself normal to this, that whole layout sketch we just did is now a straight line. So occasionally when you're doing this, you need to come in here and kind of work at this kind of slightly angled thing so you can kind of see what's going on. So what do we really care about? We care about kind of the width stack up. So maybe what we should do is draw in, here's how I'm going to do it. I'm going to go into these sketches that we did before, and I'm going to add points onto the width dimension, basically, of how big almost all these circles are. So basically on the left and right hand side of every circle, we're dropping in points. I have a keybind for points, that's the Z button on the keyboard. Points, points, points everywhere. What else? You know what's bothering me? The fact that we never did outer diameters. So we're just going to come in here and do outer diameters. These are all 20 dp gears, so the outer diameter is 0.1 inches in radius bigger than the other one. Okay, or you know what? Even better. Let's do it. Just as even better. Again, I'm liking this stacking dimensions thing, so I'm going to go back here, sketch on the front plane, and offset these as their own sketch. It's like if you've ever done Photoshop and you want to have like a lot of layers so you can hide and show things.
Why are you offsetting the shot?
The sprocket.
Oh, is that the sprocket? Yep. Okay, good catch. So now we have this outer diameter, and if we really were good, we would have not done this extra dimension here, and instead we would have made this and that co-radial. So now we're defining this. Okay, cool. So what did I want to do? A layout sketch, right? So maybe we go back before the boss extrude. We do a top-down view. And now that I have all these points, I can kind of come in here and do rectangles. And I can make the rectangle, in this case, let's do it like this. I'll make the origin, the front edge of this top-down view be the face upon which the motor mounts. And you can just kind of drop these relevant rectangles. So the length of a sim motor, I think, is like 3.5 inches or something. We need some OD, some points on the OD. So I'm back over here, dropping in points. I knew this is familiar to you too, right?
Yeah.
Okay.
Show one of the
We're almost done. Okay, layout sketch. So that was kind of the you know, let's call that the motor, and then it's gonna have a 1/4 inch plate. So we'll make this and this collinear. We'll make this plate 1/4 inch thick. We'll call this 1/4 inch AL aluminum plate. I guess if I was really being good about sim body length, LG. Oops, LG. Okay, then what do we have? We're going to have bearing bores. So maybe those bearing bores are here and here. They're a 1/16 of an inch thick. We can say this is bearing flange length. Make all these lines equal to each other. Then I can make these points relative to, let's hide the gears, There's the bearings. Okay. Did I not put points on my bearings?
No, but the bearing OD is not flange OD.
Oh, yeah, you're right, Anuj. Okay, good. This is why I have Anuj here, because he's smart. But what I can do is I can dimension the bearing OD, which I think is 1.25, or sorry, it's about 1 inch, for a 3/8 bearing. So I keep fat fingering my way out of there. And over here, this is, I think, 1.25 inches for the bigger bearing. I can select midpoint, select the midpoint of the circle, hit the vertical relation, and now it's straightening everything up. So this is, doing this multiple view layout sketch, we're starting to reach the point where it's like, this is taking a lot of time to lay all this stuff out. And this is when you want to start doing that decision in your head of, am I really going to do this as a multi-body thing? Or should I just do the bare minimum and move on? You know, you don't have a lot of time in FRC to make the best perfect parametric models. So you kind of have to pick and choose where you're going to devote your time. If you're going to do all this fancy layout sketches, you're investing a lot of time up front, and maybe you won't really see the returns of that down the line if you don't end up wanting to change the thing that much. Anyway, we're just going to go fast, relatively fast here. The next gears are, I think they're 1/2 inch wide, including the nubs. And we can, again, just frickin' draw in a construction line down the midline of each of these. Select midpoint, drop it onto there. Make this maybe coincident, collinear with that. Okay, and then there's going to be another gear that's also 1/2 inch wide. It's also along the midline. If we wanted to, we could come in here and do the vertical relations to get the outer diameters of the gears if we care. And then maybe we do a frickin' another flange. Select midpoint. Coincident. Make those collinear. And draw in one more gearbox plate.
I have a question while you do this.
Yeah.
Wouldn't having them be touching create a lot of friction? Or is this just this isn't modeling in the nubs, but the 1/2 inch width would include the, so if you've ever seen it here, there's the little nubs on the sides. So yeah.
Okay, I think we're doing fine. So all of this entire thing literally was just so that I could get 2 rectangles, and it turns out they have to be 1.125 inches apart. Okay, that was literally all this just to get the length of that standoff. So now I have this sweet top view layout sketch. I have this front view layout sketch. I'm gonna call this top layout. Scroll forward. I'm going to edit this boss extrude to match what I did in the layout sketch. So instead of doing a mid-plane extrude, here's the really key part to get really good at this layout sketch multi-body stuff, is you have to adjust the from and the direction limits on your extrudes. So if I change the from and I change it to say vertex, and then I choose the start vertex of the thing, then I change the end direction to be up to vertex, and I choose the end vertex. Now it's going to extrude my plate, matching the sketch I drew here, and then the direction and the location of it is driven by that top layout sketch. And we're about to do the same thing again with the standoffs. So we'll click the check mark. Now we have a plate that lines up with our top layout. Let's do the standoffs now. Okay, fine. So we have the standoffs, we extrude, and we can maybe just again do, here we can do from sketch plane, and we can do up to vertex, and we'll choose the other plate on the other side. And then we're going to uncheck merge result, and we're going to get a bunch of little individual bodies. This is a little annoying for me to have to go whole wizard them all, so I'm actually going to come in here and I'm going to draw in their inner diameter, because these are going to maybe be off-the-shelf standoffs. Yeah, I know. But this might be a number you get from McMaster-Carr or something, right? Like if we went on to McMaster and we looked up standoffs, and we guess they're really called spacers. We want aluminum ones, inch, outer diameter 3/8 for number 10 screw. It tells me the inner diameter is 0.192. And look, they sell one that's 1.125 inches long. Awesome. We don't even have to make any standoffs. So 0.192 is the inner diameter. Hit the check mark, exit out of here. Now we have our 4 standoffs. So again, look, we have multiple bodies now in the solid bodies folder. We have the plate, we have each of the standoffs. We're chilling. If we want to finally finish this up, we can do a sketch. This is kind of personal preference. I guess I'll sketch on the end of this standoff, and we'll do the mount plate, which is basically going to involve grabbing these standoffs and then kind of grabbing here. Boom, boom, boom. Catting on the fly. So much fun. Start making things tangent. Drawing all our connecting lines.
Alternatively, you guys, what you do is you keep everything on the same sketch plane, and you do the start from and up to vertex thing using your top view to figure out where everything is. It's just by putting it on the end of the standoff, it allows them to use it ends up being the same thing, really. Yeah, personal preference.
Okay, so now we can extrude, and we can do up to vertex, select, up to vertex, select that, and now we have our mount plate. I missed doing, let's convert entities, oh my gosh, convert entities, okay, cool. So now we have the mount plate. Oh, we messed up. I merged bodies. Look at that. It turned this into this crazy billet part. We don't want that. Edit this feature. Uncheck merge result. Hit the checkbox. Sweet. Okay, lastly, we just want to do the holes. So this one is going to have clearance holes. This one is going to have tapped holes, except for the spots where the sims go, because the sim is tapped. That will want tapped holes also. So hole wizard, tapped holes, or clearance holes, number 10, positions over on this face. It's going to be here, 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 here. Feature scope, unselect that. Select the one body that they're going to have feature scope on. Checkmark that. Boom. So now they didn't cut through my other plate. Let's do the next one. Hole wizard. Selected bodies is going to be this guy. Positions, that face, here and there. So those are the other. Oh no, I did that wrong. Sorry. It's going to be here and here. And then maybe lastly we do tapped holes. Tapped hole number 1032 through all. Feature scope, select the plate that we want. Positions, click on the face. Drop it in location.
Look at your bottom left hole on the back plate.
Oh, good catch. This ridiculous thing is dimensioned onto the edge of that circle instead of onto there. Okay, good catch, Anush. Okay, cool. So now we have 2 gearbox plates with standoffs and all the necessary holes. I guess if there was one other thing we needed, which was tapped holes for the mounting, was in this one. Again, remember we defined them all on these guys. Checkmark that. Okay, And again, it only went through this part and not that one. So this is cool. Now we have our gearbox. Now we want to turn this into individual parts so we can feed them into a CNC router or something, and it will machine them. So what are the different ways? I've shown you one way of doing it, right? Everyone kind of remember what I'm gonna do here? I can right click, save bodies, select all of these, give them all file names, blah, 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 right? I'm not gonna do that because when you do this style of just exporting the bodies, what ends up happening is you're literally only exporting a single body. Let me do it on this plate here. If I do the insert into new part, we name this mount plate solid body. I showed you guys this before, but really what you have here is just the solid body, and it is showing these threads, but they're treated as these cosmetic threads, which are kind of annoying. And if I then go and try to, like, maybe this wasn't a CNC part, maybe this was a manual part. If we were to make a drawing, I'm pretty sure that this doesn't like the hole call out. It'll say 1032 tapped hole, but if I use the hole call out button, yeah, okay. So if I want to add any of these other hole call outs, all it says is the diameter of the hole, because that's all it knows is the solid body geometry. I did not import any of the fancier hole wizard data into this. So that's why most of the time I don't really like to use this save body as part. Instead, what we'll do is kind of like what we did with the layout sketch. We're going to make a new part. I'm going to call it motor plate 2. We're going to insert part. We're going to insert our layout sketch that really is a multi-body part now. And then here, this is important. So which of these checkboxes do we select? We do want the solid bodies. We don't need the unabsorbed sketches anymore because we did all the defining earlier. And we definitely want the hole wizard data. So now we click the checkbox, and it inserted the entire multi-body part, all the bodies. If I go into here, you see we still have the folder full of all the bodies. However, here's where the trick comes in. If I come under here and I type in keep, delete keep body is a feature that we have. Click on that, change this to keep bodies, and select the correct body and click the checkbox. It will get rid of all the other bodies and leave you with just the one body that you want. The reason why I like this, there's two reasons. One, it's faster. As you'll see me just now, I'm going to do it for the motor plate. Okay? You'll see it one more time. We did the insert and the keep bodies. These are two features that are basically going to stay the same for all the other parts in my assembly. So if I now go under File, Save As Copy, and Open, I just change this to the mount plate, number 2. It's now going to open up the mount plate. It still looks like the motor plate because unless I adjust this feature, edit feature, unselect that, select that one, checkbox. So that was actually, in my opinion, faster than doing any of those other methods. Is because you can just save as copy, change which bodies you're keeping for each part, and it moves it over really fast. Now, let's demonstrate that this also preserved the hole wizard data. If I make a drawing from this part and drop it in and do hole call out, you'll see, oh yeah, there we go. Quantity 4 of this drill diameter, and then you tap it to 1032. It's got the hole wizard data. It makes your drawings way better, blah, blah, blah. Okay? So that is, in essence, I would say there are two equally valid ways of doing this multi-body modeling. The first of them was what we were doing here with number 1, gearbox layout sketch. So this is where you just sketch the key geometry in a single master sketch, a layout sketch. Then you insert that sketch into individual parts, and in each part you do multiple boss extrudes, hole wizards, anything you want. So you're really building the part at the part level. That was what we did first. What we did second was we did a multi-body part where we built all of the bodies in one part, which is better especially when you want to do things in 3D, like those standoffs that relate their length based off of other stuff. And then you export each of those bodies into individual parts using the insert part and then the body keep function. Two different methods, layout sketch, multi-body part, two different styles. Let's talk about the pros and cons. So in the layout sketch, the pros, you can have one layout sketch and then you can have multiple people working on different parts all in parallel. Someone can be doing the pocketing for the motor plate, someone can be doing the pocketing for the mount plate. Somebody can be making the extrusion and part drawing for the standoff. So the layout sketch is better because you more quickly parallelize the nitty-gritty modeling of all the little features each of the parts need. The downside of the layout sketch is that you need to do a lot of fancy sketching all in one sketch, one body. You need to kind of think about it all in sketches. You never get to go to 3D in the layout sketch. And the other downside is it is really hard to do fancy 3D things, like extruding a curved fillet surface and extruding like up to that curved fillet. That's something you will never be able to do in a layout sketch. You'll have to do that in a multi-body model where the two things relate with that method. So then, what are the pros and cons of the multi-body style? In multi-body, good job. In multi-body, you are designing all of the parts at once in one part file. That is good if you're really fast and you're the one designer that is super amazing, but it's bad if you want to parallelize anything. You can only have one student working on this one awesome master body model, and nobody can help them, because if you try to send the file around, all the file versions get mixed up, GrabCAD, PDM, it doesn't know what's going on. So it's not as good from a parallelization collaboration standpoint. But the pros is that you get to do 3D geometry all at the same time in one big body. And that's kind of the end of my talk. So does anybody have any questions on any of those things?
After this is done, could you guys like come to the atrium so we can do a quick feedback and some wrap up stuff?
Sure. 4:15? I think was the scheduled end? Yeah. Okay, cool. So I'm happy to answer any questions about this, about 254, about SolidWorks in general, anything you want. Yeah.
Could you do like a 3D layout sketch and then export that in covers so you get the...
Yes. So if you're asking, like, if we took this dude and we stopped it right here,
Yeah.
could I then go and import those and do the layout sketch off of that? Yes, you can. It's kind of, I would call this layout sketching still. It's just you're doing multiple views. Yeah.
How does 254 do is like CAD training for incoming members?
We have some 254 students here. I'm training some of them right now. How else do we do CAD training? A lot of times we try to excite our students early on by having them design something really cool, like a gearbox. And they think that it's amazing and it's going to go on a robot or whatever. It probably never will, but at least it's a very comprehensive start to finish design process. And we use that even if they're really slow and we're teaching them, like, here's the circle button, drop the circle here, do the smart dimension. it's still like, I think the students enjoy that better than doing some other, like the built-in SolidWorks tutorials or following a video online where they're making something that feels meaningless and arbitrary. So generally what we do is every night at Build, starting in the fall thus far, we've had one of our student leaders who is doing CAD workshops trying to teach students how to do a full gearbox from start to finish, which start really meaning like an Excel spreadsheet where you're picking the torque speeds and numbers of teeth and stuff, and going all the way through to an assembly that could go into a robot somewhere. And so we've been doing that for like 3 hours a night, 3 nights a week with our students, and they're starting to just now finish their assemblies. Sure, yeah, that was a good question. Anybody else have any other questions on anything? Okay, let me do this. How many people here would say they understood the concept of the layout sketch versus the multi-body and the pros and cons between the two? Raise your hand if you feel like you kind of got that. Okay, to some extent. Raise your hand if you're kind of, just getting into SolidWorks, this is, you're just getting started and this talk was kind of a little bit over your head. Okay, I'm just getting a gauge of the room, that's all. I'm not picking on anybody. Yeah, okay. Have I considered doing a TED Talk? This is not TED Talk material. You want to be like doing an inspiring, like save the world, rah rah.
Revolutionize computer aided design things.
Oh yeah, okay, sure. And then how many people think, although maybe you yourself are not the person that is quite yet gonna do all of this, how many people think they understand the usefulness of these two practices and could at least kind of relay this information back to their mentors or whoever else on their team? Anybody feel like they understand the usefulness there? Could I repeat the question? Yeah, raise your hand if you feel like you understand the usefulness of these two techniques. And even though you yourself may not feel as confident in doing it, you think you can roughly explain like why you came to this talk and kind of what it was about. Yeah? Anybody? Okay. A couple people? Okay, cool. That is good feedback for me, so thank you for that. Does anyone have any other questions about CAD or 254? If not, we can just wrap early. I don't mind. Yeah?
Would it be beneficial in any way to like import gear models from Vex into the assembly?
Yeah, the question for the recording was, would it be beneficial to import like gear models from Vex Pro and put them into your multi-body model or your layout sketches? I would say that the answer is yes, it can be useful. The problem is it's not very easy to make that parametric, meaning you update the gear model in the sketch and it'll download the correct new gear model and put it in your part. Or vice versa. If you put in a new gear model, it'll design the sketching around that. It's really hard to get that to link up, especially for things that aren't in the SolidWorks toolbox, like custom fancy Vex Pro gears. So generally, instead of inserting the part, I just redraw the key geometry, the pitch diameter, the outer diameter, the width, and I use those key sketches in all my fancy modeling. So then if I need to go in and change the diameter of the gear, I just change it only in the sketch. And at the end of the day, you're still going to have to go into the assembly and make sure you've pulled in the right gear models. But yeah, it's really hard to do the insert part and get that to work correctly. But that was a good question. I've tried to do it. It's tough. Anything else? Yeah?
What do you think about like, do you guys like create like folders on your computers where you have all of like the gears that you use, like and like screws and stuff?
Yeah, that's something. You're just having a part library for common FRC things. that's something that we have tried to do, and we did reasonably well, but then stopped doing halfway through the season and messed up and got all bad.
So,
Go ahead, Noosh.
for us, the issue was that we decided, so we use GrabCAD on our team. So we decided, you have a GrabCAD project for your 2019 robot, and then you made a separate project which had all of our cost parts, because our old robots still reference that same project and all that stuff. The issue was whenever you tried to update something or send it out, people had to update both folders if they added any new cost parts, and if you didn't download the cost folders before opening it, you would like lose your the assemblies like would have suppressed missing components and would break. So it was really just like there wasn't enough diligence on our team and people weren't really using it properly, so we're just like, screw it, getting people to do this is too hard. Let's just put the cost parts inside the project.
Yeah.
What we're thinking about for this year is instead of making the cost library be a separate folder, we'll just make it be a folder within the 2020 robot project, so that when you only ever update 2020, but the cost library there still is a cost library.
Yeah. You have to click one less button, and it guarantees every time you upload your latest assembly, it'll also guarantee that those COTS parts are chained with it. Yeah, there's some other good design libraries out there. Team Spectrum has uploaded one online. I think 3476, is that right? Yeah, maybe. I forget their number. But Spectrum's CAD library is pretty good. It doesn't really do screws perfectly, but it has like all the VexPro electronics you'd need. It has all the motors. It has versaplanetaries and off-the-shelf gearboxes from West Coast Products, stuff like that. So that's a good starting point. Okay. Any last questions? You can stay and talk to me after, or talk to Anuj. Let's wrap it there. So thank you guys for coming to my talk. I hope you have a great time. If anybody has any questions, you can also email me at andrew@team254.com. That's my Team254 email. So you can email me if you have any other questions about the team or the CAD practice or this workshop or anything like that.
You might want to clarify that it's not all caps.
Emails don't care. Great. Thanks.